Hi there, thanks for clicking on and watching. Welcome to this year 2 video for Maths A level looking at vectors. So the things we're going to look at are the distance between 2 points, the I, J and K notation, the magnitude of a vector and the angle that it makes between coordinate axes, solving some geometric problems and some applications to mechanics. So this video is designed to go along with the booklets that accompany the Dr. Frost PowerPoints. I'll put a link to the file for the booklet in the description, so if you've not got one of those you can download it, fill it in and make some notes as we go along. I'll also include chapters in the description, so if you want to skip to a certain part in the video you can just click and go directly to that section. Okay, let's get started. So here we're going to start with the distance from the origin, which is going to be the magnitude of the vector. Remember, vectors have magnitude, which is their size and direction. So if we've got a coordinate 3, 4, that would be the position vector 3, 4, writing it as a column vector, which is 3 along and 4 up, which then will give us that right angle. So the size of that vector, which starts from the origin and gets us to the coordinate 3, 4, we're just going to use Pythagoras' theorem. So D would be the square root of 3 squared plus 4 squared. Now, if you know your Pythagorean triples, 3 squared is 9, 4 squared is 16, add them together 25, square root of 25 is 5. So 3, 4, 5 is a Pythagorean triple. So how about in 3D then? So from the origin, if we use the coordinate 3, 4, 12, which is the position vector 3, 4, 12. So it's not really to scale because this is 3 along the x, which looks much bigger than this 4 along the y, and then we've got 12 up the z. So the z axis when you're in 3D goes vertically up. So how are we going to find the length from the origin to the end of that vector after we've done 3 along the x, 4 along the y and 12 up the z? So it's the back of that box. So what you need to do is find the length of that diagonal along the base. Now this triangle here is a right angle triangle on the base, and we're going to just do Pythagoras to get the diagonal of that rectangle on the base, which is just going to be the same as what we've just done, 3 squared plus 4 squared, so that length would be 5. But then you would be putting that length 5 into Pythagoras' theorem again, because we want to be working in this right angle triangle that is sitting upright through that rectangle. So you'd be doing 5 squared plus 12 squared to get the length there. But instead of doing it separately as the two triangles, the one on the base and the one that's upright, how did we get this 5? It was the 3 squared plus the 4 squared, and we're going to be squaring that again. So all you need to do, D is going to be 3 squared plus 4 squared plus the 12 squared, and then take the square root, because this will give you the 25, and we're going to be squaring that 5 to get the 25 to then put it with the 12. So in 3 dimensions, it's just an extension of Pythagoras' theorem. You're just going to be doing x squared plus y squared plus z squared, and how we write the magnitude of A is we use those modulus lines, and that's going to say that's the size, which is the length of the line. So now we're going to have a look at the distance between any point. So not just the origin and a point, just any point. So first of all, before we have a look at it in 3D, let's just have a look at 2 points in 2D and see what's going on. So say I've had the point 2, 1 and the point 5, 5. So there's my 2 points. If I want to find the length of that line, all you need to do is use Pythagoras' theorem. So in order to find the length horizontally, it's going to be the difference between the x coordinates, and that is the change in x. So you can see this little symbol here means the change in x. So 5 minus 2, that's going to be 3. The distance vertically is going to be 4, and I've got my Pythagorean triple again, so the length of that line is going to be 5. So without drawing the picture, if I just had the point 2, 1 and the point 5, 5, then you're just looking at the horizontal coordinates, the x coordinate, and seeing what the change is there. That's going to be 3, and then looking vertically to see that the change in y is going to be 4, and it's the 3 squared plus the 4 squared that you put into Pythagoras' theorem to get the 5. Now, it doesn't really matter whether we do 5 take away 2 to get that 3, or 2 take away 5, which would be minus 3, because you're going to be putting it in here, and minus 3 all squared is still going to be 9. So when you're looking at these 2 points here that were in 3D, all you need to do is to find the horizontal distance. You're just going to look at the 2 x coordinates and find the change in them. So horizontally along the x, we're just going to go a difference of 1, and putting it into Pythagoras' theorem is going to be 1 squared. Then look at the y, and you're finding the distance, which is just the gap between those 2 numbers, and it doesn't matter which way round because you're going to be squaring it anyway. So if 4 was on the number line and minus 1, the gap between those 2 numbers is 5, so it's going to be 5 squared. And then in the z, just look between 12 and 7, which is also 5, and then we're going to find the distance by taking the square root, just Pythagoras' theorem. 5 squared 25, 5 squared 25, and then 1, so that is going to be the square root of 51. So having a look at these ones here, the distance between 0, 4, 3 and 5, 2, 3. Under here you can see the distance horizontally is between 0 and 5, so that gives us 5. Then between 4 and 2, then you could just look at 4 and 2 and just see that the difference is 2. So you could 2 squared and minus 2 squared is still going to be 4. And then the distance in the z, well, there's no change, so that's going to be the 0. And then square root of all of that is going to be 29. So the next one between 1 and 2 is just going to be 1, 1 and 1, 0, 1 and 0, 1, square root of 2. Then the last one between minus 5 and minus 2 is a gap on a number line of 3, so 3 squared. 2 to minus 3, the gap between those 2 numbers is 5, and then 0 and minus 3 is going to be 3, so the square root of 43. So testing your understanding so far, if we're trying to find the distance from the origin to the point 777, all you need to do is apply Pythagoras' theorem in 3D. It takes each of the components in the 3 dimensions, 7 squared plus 7 squared plus 7 squared, take the big square roots, it's 7 root 3. Now the next question, you're trying to find the distance between A and B, given that these are the 2 coordinates of A and B. So again, applying Pythagoras' theorem, but now because we're not from the origin, what you need to do is to find the difference in the x coordinates, and 5 minus 1 gives you the 4. The difference in the y coordinates, and that's going to be k minus 3. You can do 3 minus k or k minus 3. It doesn't really matter because you are squaring the distance. So putting the k first is just going to be easier when we get on this line. And then here, the difference in the z coordinates, if we do minus 3 minus minus 8, you're going to get minus 3 plus 8, and that gives us the 5. Now when we take the big square root and apply Pythagoras' theorem in 3D, we get the answer 3 root 10 given to us in the question. So now you just got to square out this bracket, so you're going to get k squared minus 6k. Sort out with the numbers with the 16 and the 25. It's going to give you 50 with that 9 that you're going to get there. Now if you square both sides, you're going to get rid of the square root on that side. If we square this side, the 3 root 10 is going to be 9 times 10, which gives us the 90. And then all to one side, you've got a quadratic, and we're going to get the 2 answers, minus 4 or 10. So notice in this textbook question, in exam questions, they do actually give you a clue, the values of k being plural. You know, it's no surprise that we've actually got 2 answers. So just looking at the notation now, you should be already aware of I and j from year 1 work. It's 1 unit in the x-axis direction and j 1 unit in the y. So 8 minus 2 could be written as 8, and this is just I and j, and so that's the column vector 8, 2. So unsurprisingly, in 3D, we just call it I, J, and now K. So K is 1 unit in the Z direction. So being able to toggle between the two notations. So in a column vector here, we've got 1, 2, 3. So in I, J, K, that would just be I plus 2J plus 3K. So minus 7, 3, 0 is minus 7I plus 3J and then no K. 3I for this one minus 1K. Now going the other way around, 4J plus K is going to be 0I and then 4, 1. I minus J is going to be 1 minus 1, 0. Now A to B, the journey A to B, given that these are coordinates, so if they're given coordinates that going along horizontally instead of a column vector, then that means they've come from a common origin. So to get to A, we're doing the coordinates 1, 2, 3, so that might be the vector A, and then to get to B, we're doing the coordinate 4, 0, minus 1. So how do we get from A to B, which is this direction? We'd have to go back down A and then along B. So when you've got that common origin, the journey A to B is always B minus A. Just put in the minus A second, just makes it look a bit prettier having the negative one after the B. And with the vectors, it doesn't matter which way around you take those journeys, they're always going to end up at the same place. So if we do B minus A, treating these coordinates as column vectors, then in the x-axis direction, we'd be doing 4 minus 1, which would give us 3, 0 minus 2, which is minus 2, and then minus 1 minus another 3 would be minus 4. Now if we're given these column vectors, A is 2, 3, 4, B is 0, minus 1, 3, then 3A plus 2B means we need to times everything in A by 3 and everything in B by 2 and then add them together. So it's going to be 3 lots of 2 plus nothing, which is going to be 6. 3 lots of 3, 9. 9 minus 2 is going to be 7. 3 lots of 4, 12, plus 2 lots of 3, 6. So that's going to be 18. Here, looking at some more examples, we've got to find the magnitude of A and hence find the unit vector. Now, the symbol for unit vector is this A hat, and a unit vector is just a vector in the same direction, but instead of being length, whatever the vector is, it's going to be length 1. So first of all, we need to find the magnitude, and the sign for that is these modulus lines. So we're just going to apply Pythagoras' theorem as we've been doing. So it's 2 squared plus 1 squared plus 4 squared, and take the big square root. That would be the length of the line, so that's going to be the square root of 21. Now the vector goes in this direction, 2I minus j plus 4k, so if we want something that's going to go in that same direction but be length 1, the unit vector is the given vector A, then divide by the magnitude. Divided by how big it is going to reduce it down to, instead of being length root 21, it will be length 1. So it's just going to be 1 over root 21 times the 2I minus the j plus the 4k. Okay, so that would be the unit vector. Now in this next example, we've got A, 2 minus 3, 5, B, 4 minus 2, 0. Is 2A minus 3B parallel to 4I minus 5K? So what is 2A minus 3B in the horizontal direction? It's going to be 4 minus 12, which is going to be minus 8. Then in the Y direction or the J direction, minus 6 plus 6, so that will be 0. And then in the K direction, we're going to have 2, that's 10, and minus 0, which will be 10, which is 2 lots of, or minus 2 lots, sorry, of 4, 0, minus 5. So because it is a scalar multiple of the vector that we're saying it's parallel to, it is therefore parallel. Having a look now at the angle a vector makes with each of the axes, whether it's the x, y or z axis, how could we work out that angle? We're just going to form a right angle. So here we've got the angle that this vector with the blue line A makes with the x-axis. So we call the x-axis this distance x along, and then the vector A is going to be the hypotenuse. So the distance along the axis is adjacent to the angle, so we're going to use cos, and cos is adjacent over hypotenuse, so cos of the angle that the vector makes with the x-axis is just going to be the x coordinate divided by the magnitude of that vector. And you can do the same thing for any of the axes. So let's have a look at this example here. You've got a being 2i minus 3j minus k. The modulus or the magnitude of a is going to be, just putting all those numbers into Pythagoras' theorem, root 14. So the angle it makes with the x-axis is going to be the x coordinate or the x component, the I component, 2 divided by root 14 and inverse cos of that. Similarly with the y, the minus 3 over root 14, inverse cos of that. And then in the z, the minus 1 over root 14 and inverse cos of that one too. So you can pause the video here and have a go at these two examples. If you've got the booklet and write them in, I'm going to go through the answers now. So these examples from the textbook, and we're told that A and B have position vectors, these two here, and those positions are relative to a fixed origin. So they both come from that common origin. So remember, we can apply that reverse vector to get from A to B. If they both come from the same origin, you would go back down A and along B. So we'd write that as B minus A. So we've got to find that. So A to B is going to be equal to B minus A, which is going to be B, and I like to work in columns. So B is going to be 3, 4, minus 1. And A is 4, 2, 7. So taking them away from each other, it's minus 1, 2 and minus 8. And then if we try and find the magnitude of the journey A to B to find the length of the line, because we're being asked to show that the triangle is isosceles, so we need to find the lengths of the lines. So if we find the magnitude of A to B, so that's applying Pythagoras' theorem, that would be 1 squared plus 2 squared plus 8 squared. So that's going to be the square root of 69. Now what we need to do is apply the same magnitude to all the other sides of the triangle, which is going to be O to A and O to B. So O to A is just going to be O as we can take as the origin. So O to A is just this journey, 4, 2 and 7. So that's going to be 4 squared plus 2 squared plus 7 squared, and take the square root of that, and that does come to root 69. And then O to B, do the same with B, is going to be the square root of 3 squared plus 4 squared plus 1 squared, and that comes to the square root of 26. But because we've got two sides that have the same length, we do have an isosceles triangle. So A to B equals, what was it, O to A, but that does not equal O to B, so two sides are going to be the same, therefore triangle is isosceles. Okay, next question. Find the angle that vector A makes with the x-axis. So first of all, we need to find the magnitude, the length of the line. So it's Pythagoras' theorem again, 2 squared plus 1 squared plus 1 squared. So that's going to be 4, 5, 6, square root of 6. Then the angle that makes, so cos of the theta x is going to be 2 over root 6. So that angle is going to be inverse cos of that, which is 35.264 degrees. Okay, part B, by similarly consider the angle that B makes with the x-axis, determine the area of OAB. So again, now we've got to do the magnitude with B, which is 1 squared plus 3 squared plus 2 squared. So that's going to be root 14. Find the angle that it makes with the x-axis. So that's going to be cos of that angle will be 1 divided by root 14, which is 74.499. Now, drawing a diagram from this common origin O up to B, the length of that line is from the magnitude, which is going to be root 14. The length O to A is root 6. The angle that B makes with the x-axis, we can see here, is the 74.499. Similarly, the one with the for A is 35.264. Now we've been asked to find the area of the triangle OAB. So if we do a take away and find what the angle is between those two, and then because we've got side, angle, side, we're going to just use the area of triangle as half AB sine C. So if we just do 74.499, take away 35.264, the angle between them is 39.235. And so the area of the triangle is going to be half times root 14 times root 6 times the sine of the angle between them, 39.235, which equals 2.90, and that would be units squared. Having a look at some geometric problems now, we are given the four corners of a shape and we're given them as coordinates. So because we're given them as coordinates, we can use the column vectors as position vectors. So if we're asked to find the vector A to B will be using that reverse vector idea, will just be B minus A. To get from A to B, we need to go back down A and along B. So we can just write the coordinates as position vectors. So B is 1 minus 7 minus 3, and A is 2 minus 5 minus 8, and we're asked to give it in IJK form, so just working that out, 1 minus 2 will be minus in the I, minus 7 minus 5 will be minus 2 in the J, and then minus 3 minus 8 will be plus 5 in the K. Now doing the same for D to C, because we're asked to find D to C as well. D to C will be C minus D, which will be C is 0, 15 minus 10, and D is 2, 19 minus 20. So putting that in the same way, we're going to get minus 2i, minus 4j, and then plus 10k. Now you can see, looking at those two forms, that A and B and D and C are related, so we're asked to find and show that they are parallel. They're going to be parallel because D to C is equal to twice A to B, because you can just take a scalar multiple of 2 out, and therefore the lines are parallel. Okay, in part C, describe the quadrilateral. You've got two parallel sides of different length. So we have got a trapezium. Okay, next question. We've got P, Q and R are these points here, again given as coordinates, so we can use them as position vectors. Find the coordinates of the point S. Well, all we need to do here, because they're given as coordinates, we know to get from O to Q is just go along the vector here, 7 minus 7 minus 7, and then from Q to get to P, we can do that reverse vector again. So Q to P will be P minus Q, which is P, the 4 minus 9 minus 3 minus the q, which is 7 minus 7 minus 7. So that will be minus 3 minus 2, and then minus 3 minus 7 will be 4. So if we can get ourselves to r, and the vector to get us to O to r, it will be just the 8 minus 2, 0. And then once we've got to r, if we just add on this journey, that will get us to S, because we're told that it's a parallelogram, so the journey from Q to P must be the same as the journey R to S. Remember, you have to label your side either going anti-clockwise or clockwise around the shape, and we can see we've gone anti-clockwise. We've gone P, Q, R, and then S, so it's going anti-clockwise. So if we get ourselves to R, O to R plus R to S, that's going to give us the coordinates of S. So this is really going to be O to R plus the journey that we've just found, which is Q to P. O to R is going to be 8 minus 2, 0. And then if we just add on the minus 3 minus 2, 4, 8 minus 3 is going to be minus 5. No, it's going to be plus 5. God. Minus 2 minus 2 is be minus 4, and 0 plus 4 is 4. So that is going to be the position vector of S, and then we can just write the coordinates of S will be the 5 minus 4, 4. Another skill that we use with vectors is comparing coefficients. You might see this in other areas, such as when you do partial fractions, which is an upper sixth topic in pure. So comparing coefficients, you've got 3 here, x squared. The only other x squareds on the other side, because the b and c are just single x and just the number on its own. The only way to get any x squareds is to have this a, so then a must equal 3. I'm going to do that with the same with this textbook question. You've got 3i, p plus 2j and 120. Everything on the left is equivalent to pi minus qj and then plus the 4pqrk. So straight away you can see that number in front of the I, because you've just got p there in front of the I. So comparing the I component, you're going to get that P is equal to 3. Now comparing J, we can see that P plus 2 must equal minus Q. So P plus 2 is going to be 5 is equal to minus Q. So that tells us that Q is equal to minus 5. And then comparing the K, we've got 120 must equal 4pqr. And now we've found what P and Q are, so that's 4 times 3 times minus 5r. 3 5s are 15, so that'll be minus 15 times 4, which is minus 60. Minus 60 times something is 120. R will have to equal minus 2. So that's that question. Let's have a look at the next question. We've got this cube, and we've got the vertices A, O to G, and we've got H in the middle, because it's asking us to prove that the diagonals OE and BG bisect each other. Now bisect means that they're going to cut in half, so you can see that they meet. So we're looking to prove that that H is halfway along O to E and also halfway along B to G. So what we do here is we can think of two ways to get from O to H. So O to H is going to equal, now go along the blue line, it's going to be some scalar multiple of O to E. So I'm going to call that scalar multiple lambda O to E. And O to E, using the vectors on the shape, is along A, back along B, and up C. So O to E is A plus B plus C. They're the vectors that we've got on the shape. So lambda of it is going to be lambda A, lambda B, and lambda C. Now another way to get from O to H is to go along to B and then go from B to H, and going along the orange line, B to H, and then H to G. B to H is going to be some scalar multiple of B to G. So O to H is O to B plus another scalar multiple. We can't call it lambda, we might call it mu, B to G. Now B to G is equal to, you need to go along A, back the opposite way B, and up C. So that's going to be A minus B plus C. Now O to B here is going to be B plus mu, what we've just worked out, A minus B plus C. So taking that mu in, you're going to have mu A minus mu B and mu C, but you've got a B at the front. So if we line everything up, it's going to be mu A, and then what will be in front of the B? We need a whole B minus a mu, and that will be the coefficient of B, plus a mu C. Now we've got two journeys to get to the same place. We've got this one and this one. Now comparing coefficients, we can see that if we take that lambda in, the lambda and the mu in front of the A must be the same. So just looking at those first components, the first vectors, we can see that lambda must equal mu, comparing the A's. Now compare the B's. You've got lambda B here, and then in front of B is 1 minus mu. So lambda is equal to 1 minus mu. But from the A part of the equation, we've got that lambda equals mu, so this will be lambda is equal to 1 minus lambda. Take that lambda to the other side, you're going to get that 2 lambda is equal to 1, so lambda is equal to a half. Now we know that lambda equals mu, so that's also mu. So putting those numbers back in, you can see the O to H here will be half of O to E, and then here with mu being a half, you're going to go to B and then do half of that. So because it's a half, that does prove that the diagonals across the cube do bisect each other, and they meet at H, which is halfway along B to G and halfway along O to E. So next in the booklet is one for you to try, so you can pause the video, see what you get. I'm going to carry on and work through it now. So you're told that A to B is this vector here, so I'll write it on. It's 2i plus 3j plus k. B to C is going to be I minus 9j plus 3k. I've got to prove that this angle here is 105.9. So what to do first of all is to get A to C. A to C is going to be A to B, and where that vector ends, we then add on the journey B to C, and that will finish at C. So adding the two vectors that we've got already is going to be in the I component 3i, the 2 plus the 1, plus 3 minus 9, which is minus 6j, and then plus 4k. Now what we can do is get the magnitude of each of those sides, and because we have all three sides, we'll then use the cosine rule. So doing Pythagoras, 2 squared plus 3 squared plus 1 squared and the square root, that one's going to be 14. Doing the same to the next one, that's going to be 91. And doing the same to the next one, that's going to be root 61. And then cos of the angle is equal to b squared plus c squared minus a squared all over 2bc. So the angle we want, little a, is going to be opposite. So as long as this a is the one that you take away, then we're going to be using the 14 and the 61 because we need to square b, and if b is root 61, that squared is going to be 61 plus 14 minus the 91, all divided by 2 times root 61 times root 14, and if you put that on your calculator, it does come out to be 105.9 degrees. Here's another one to try, so you can pause the video and have a go. I'm going to go through the answer now. So we've got a parallelogram ABCD, so I would always draw a diagram, and then it's something to play with and to work your way into the question. So going anti-clockwise or clockwise, I'm going to go clockwise this time, A, B, C, D. We have the position vectors for A, B, and C, and we're given that A, B, C, D is a parallelogram. We've got to find the position vector for D. So we can see, because the way we label it, in order to get from C to D, it's the same journey as B to C. So if I can get myself to C, which is I've got as a position vector, and then just do the same journey that goes from B to A and add that on to C, I will get myself to D. So we need to find the journey B to A. So B to A, using those reverse vectors, is just A minus B. So A is the vector 1, 7 minus 2, minus B, which is 4, 3, 3. So that's going to give us minus 3, 4, and minus 5. So the position vector of D, O to D, is going to be O to C plus C to D. And O to C is the 2, 10, 9. And then if we just add on this same journey that gets us from B to A, so we just add on minus 3, 4, minus 5, that will give us minus 1, 14, and 4. So D has position vector minus I plus 14J plus 4K. Now the next part says vector A to X is in the same direction as A to B. Given that AX is 10 root 2, find the position of X. So if it's in the same direction as A to B, then A to X is some scalar of A to B. So it's giving us that the length of A to X is that. So we need to find what the length of A to B is and see how they compare. So the length of A to B will be the magnitude of it, and we've already found that B to A was this vector here, so A to B would just be the reverse of that, and then in order to find the length of the line, we're just going to do Pythagoras. So it doesn't matter that we have to reverse it, because we're just going to be squaring those numbers. So it's 3 squared plus 4 squared plus 5 squared. So that is going to be the square root of 50, which is 25 times 2. 25 out the root will be 5 root 2. So how does that compare with 10 root 2? It is double. So A to X is equal to 2A to B. So if we get ourselves to B and then just add on the journey that goes from A to B, then that will get us to X, because it's double the journey. So if we get O to B plus B to X, and B to X is just the journey of A to B. So O to B is going to be the position vector B, which is 4, 3, 3, plus B to X is going to be 3 minus 4, 5. So it's just the reverse of this vector here. Because we're going the opposite way, we need to go the A to B direction, not the B to A direction. So that will be 7 minus 1, 8. So X has position 7I minus J plus 8K. In this next section, last bit, we're just going to do application to mechanics. So you can see we've got all these vectors here that were given in 3D. What would be the scalar of them? We're just going to be applying Pythagoras, because the scalar is going to be the magnitude of each of those vectors. So force, acceleration, displacement, velocity. Displacement and velocity are vectors, and the name of the scalar associated with them is going to be distance and speed. So just one example on application to mechanics. We've got this mass of 0.5 being acted upon by three forces. Find the resultant. So right in the main columns, you can just add across the three components in the rows to get the resultant force and then put it in newtons. For B, find the acceleration. So you're going to use Newton's second law, F equals ma. And you're going to use the resultant force from what you found in part A to give you F, and then the mass is 0.5, so half the acceleration equals that resultant force. So all we need to do to find the whole acceleration is just double that resultant force. So that's where we've got the 10, minus 2 and minus 6. Now it does say give it in P, I, Q, J, R, K form, so you just write 10 I minus 2j minus 6k. Write it in the form that they've asked. And then part C, find the magnitude of the acceleration. So we've just got to apply Pythagoras' theorem to find the size of the acceleration. So just squaring all of them over the big square root, 140. And then part D, given that the particle starts at rest, find the distance travelled in the first 6 seconds. Well, here we're going to use our Suvat equations because we've got a constant acceleration. So filling all those in, trying to find the distance, which is s, the displacement. We haven't got v, final velocity, so it's going to be the equation that doesn't involve v, s equals ut plus half at squared. Filling all those in, we get the answer 36 root 35, and that will be in meters. Thanks so much for watching this Year 2 Pure video on vectors. Please do like and subscribe to the channel and check out my other videos, and I hope they help you with your revision.